Welcome back, everybody. This video is something known as Coulomb's law. That's the name given to this equation that we're going to go over. It is also very commonly known as the electric force or the electric force equation. So you might see either of those. Both are perfectly fine to use. We're talking about the same thing, all right? Now, team, we know that objects from our prior videos have positive charges and also objects have negative charges. If we really zoom into the atom, protons are positive, electrons are negative, neutrons don't have a charge. We also saw, team, that like most things on our scale also end up being neutral because there's roughly an even number of positives and negatives. But even so, we learned that there is this property of matter known as charge. We learned that there are two types, and because there are these two types, sometimes you have this interaction where things attract and repel. We've talked about that. Depending on when you watch this video, we might have also talked about like fields, though you may not have seen that yet. Don't worry, that'll be in the future. But regardless, what we haven't yet done is quantify charge. What we haven't done is we haven't talked about like comparing the size of one charge versus the other. A real quick example, we know that there are large masses and small masses, a train versus a feather, all right? We could even talk about how a train maybe is able to apply more force or something, but we have to also be able to quantify the amount of size, like using mass, using kilograms or grams. Likewise, we can talk about attraction and repulsion. We can say one thing has more charge or less charge, but we haven't yet talked about how we actually measure charge, and that's important. Because if we're going to try to calculate the amount of force that is exerted on things, we need a way to actually get a number for how much charge there is. So that's where we're starting with this part number one here, and then we'll get into the equation, okay? So we're trying to figure out a little bit beyond just positive and negative, beyond just big or large, but to measure charge. And first, again, team, charge is something that we don't come across all the time, which means it's a little less intuitive, and it also means there are some vocab words that you might not be as familiar with compared to, say, force and mass, which you may have already known about a little bit just in life, besides watching this video. Here is one example of a word that is less intuitive. There's a very good chance you never came across this word before. In science, we measure charge in something called coulombs. That's how you pronounce that. You don't have to write out coulombs. We could just abbreviate that with uppercase letter C, just like instead of writing out kilograms, we could just write kg. I have kind of a silly way to remember coulombs. I found this picture online, and this picture is showing a really hip llama. It looks like because of their glasses and because of this background image, I think of the 1970s. I'm pretty old, even just looking back at that. But team, I think of coulombs, and I feel this image pops into my brain for two reasons. I said that this is a very hip looking image, but to be fair, people nowadays don't really say the word hip. They might say something is looking cool. And we are in the age of acronyms, of abbreviating things. Maybe instead of trying to text out the word llama, you abbreviate that to be, well, not llama, that's two syllables, that's too much. This looks like a lom if I just remove that second syllable. So I look at this picture and think, oh man, that is a hip looking llama, or that is a cool lom. But that's how you pronounce this word. This is what we measure charge with, coulombs, all right? Now everybody, just to get things even weirder, a coulomb is 6.24 times 10 to the 18 electrons. That is 1,000 billion electrons. In fact, 6.24 of those. A coulomb is a huge amount of charge. And the reason why it turns out being such a large number is because, team, early scientists were messing around with electricity and charges back in like the 1800s, well over 100 years ago. Many of them didn't even know what an electron was at the time. It hadn't been discovered yet. But like trying to get little sparks and shocks and electricity flowing in the 1800s, it turns out that actually takes a lot of electrons. So they defined this word coulombs, this amount of charge, before actually recognizing that the source of charge is from electrons and protons. You end up with this huge number. It is the same as saying 6.24 quintillion. It's a lot of electrons. This actually might be fatal. If this amount of charge was passed across your heart, that could kill somebody. So one coulomb, just one of them, is actually a huge amount of charge. But anyway, that's what we got. Scientists love sticking to convention, so unfortunately it's not going to change. The math symbol for charge is lowercase letter q. C is already taken for other things in physics, so they like to use different variables as often as they can, so they use q for charge, all right? Now, protons and electrons have equal and opposite charge, okay? The charge of a proton is positive, a charge of an electron is negative. We already know that, but it turns out even if we measure the actual charge of each of these two things, they have the same amount. But remember, we say that protons are positive and electrons are negative. So the amount, the quantity of charge is the same, 1.6 times 10 to the negative 19. I'll talk about this number in just a second. But notice, a proton is a positive version of that number, and an electron, electrons have a negative charge, is the negative option. This number right here, this 1.6 times 10 to the negative 19, that is a teeny tiny amount of charge. Why? Again, the way that charge was was defined, 1 Coulomb, it's a huge number of electrons. So actually one individual electron or one individual proton actually has a teeny tiny amount. Careful, if we're talking about a problem that says you have a proton and an electron, the charge that you're plugging in, it's these numbers right here. You're not plugging in 1 proton, you have to plug in the number of coulombs. And in this case, for protons and electrons, they are in fact very, very small numbers. All right, well, let's get to it. Team, again, we've talked about this idea of attraction and repulsion. If we have opposite charges, they like to go towards each other. If they're the same charges, they like to go away. That means we're dealing with objects, particles that are accelerating. And if you remember Newton's second law, if I have things that are accelerating, that actually means, team, there has to be a force. So when we talk about things attracting and repelling, we are fundamentally talking about a force between these charges. To be honest, depending on if you're in my own class and depending on when you watch this, we might have actually have investigated the role that different charges and how far away they are comes into play for determining the amount of force. But regardless, we're talking about a force. That's what we're dealing with when it comes to things attracting and repelling. So the name of this equation, really that's what it is. It's a force equation. It is classically known as Coulomb's law, but it's an equation. Also, you could just describe this as the electric force equation. It's the force between electric charges. Either of these names are interchangeable. It doesn't matter which one you use, but the electric force between charges, it is equal to, oh man, this right here. The electric force equation, Coulomb's law, is a large equation. You have things being multiplied on the top, you have division in the bottom, you have an exponent in the bottom as well. This diagram is corresponding to this equation. So let's look over this, okay? Q1 and Q2, if you remember from a couple pages earlier, that is representing the charge. The electric force is always between two charges. Maybe this is a proton and an electron. It doesn't have to be protons and electrons though. I could have a large object that I just gave a huge amount of positive charge. I could have a big metal block that I loaded up with electrons that has a large negative. So it's not just protons and electrons, but Q1 and Q2, those are representing the two objects. D is, you may have guessed it, is representing the distance. Careful, it is distance squared over here. All right. And then the last thing that we haven't talked about yet at all is this lowercase letter k. K is known as Coulomb's constant. Okay. K is just what it sounds like. It's a constant. It is a number that is never changing. The number for k is 9 times 10 to the 9th power, all right? You never have to memorize that. That equation will be given, at least if you're in my own class, and it's also never changing. Whenever you see k, you are always plugging in 9 times 10 to the 9th. Now, just going back real quick, let's say there was a math problem and it said you had a proton and an electron, 1 proton and 1 electron. Just to try to hammer this point home, you would not plug in 1 and -1 because the charge of an electron is, remember, it's amount of coulombs, okay? You have to use the number of coulombs. You're not ever like writing in the quantity of protons. You have to use the amount of coulombs, the amount of charge. That is often a pitfall for some students that I have in the beginning stages, okay? So team, when we've been talking about this idea of like charges repelling, opposite charges attracting, just know fundamentally that is because of a force that is acting on them. We could just say attraction and repulsion, but now we can actually calculate how much force that is, okay? And we can use this equation, this Coulomb's law, this electric force equation, to actually figure out how many newtons of force is causing these particles or these larger objects to either attract or repel, okay? Team, depending on if you like continue your physics career or if you look up this information online, just know you might see this equation that has absolute value signs. And if you're not sure what that means, that's actually okay. Sometimes in my own class, we might be plugging in, say, a negative number, depending on if our charge is negative. We might be plugging in positive numbers if our objects are positively charged. We're just going to keep in those negatives and positives, but just sometimes this equation is a little more officially written down where you don't use the negative numbers, but that's just getting into a little more detail than we're going to worry about in my own high school class. But maybe just be aware that you might see the equation written slightly different, but overall it's 3 things being multiplied in the numerator, then we are dividing by the distance in the denominator, and that distance is being squared. Okay, my last little page, just again everybody, if you're in my own class, we're going to do some practice problems. I'll be able to assist. All right, here I have an old style of notes that I give to students, so even in more recent years you'll probably see something very similar where I'll give you the equation, I'll define things, okay, I'll write down the amount of charge. It is your job to be able to practice applying this equation. All right, so that's what we call Coulomb's law or electric force. It's an equation that is calculating the force of attraction or repulsion between charges. That's all I got. Thanks a lot for watching this video.